Hey everyone! So today we're going to take something that looks, let's be honest, kind of boring. A grid of numbers called a matrix, and we're going to treat it like a secret agent. We're on a mission to uncover its secret identity, find its hidden personality, and figure out its secret power. Let's get started.
I mean, really think about that for a second. What if that grid of numbers wasn't just a bunch of data, but actually had a character of its own? A fundamental strength, a direction it always wants to point in, no matter what? Well, that's exactly what we're here to find out. We are going to unlock the secrets hidden inside the matrix.
All right, so our first piece of this puzzle is all about measuring a matrix's power. And our very first clue is a single, simple number called the rank. This is our way in, our entry point to understanding what a matrix can really do. So what exactly is rank? Well, put simply, it's the number of truly independent rows a matrix has after we clean it up and strip away all the junk, all the redundant information. It's just one number that tells us how many unique dimensions this matrix can actually influence. You can think of it as a pure measure of its fundamental power. Okay, so how do we find this essential number? I mean, you can't just look at a matrix and guess. We have to simplify it first. Kind of like clearing away a bunch of smoke to see what's really there. And we do this using a set of tools called elementary row operations. These are just simple moves like swapping rows around or adding a multiple of one row to another. Take a look at how this actually works. We're using that top row as a tool to create zeros in the rows right below it. And notice what happens to that bottom row. Poof, it becomes all zeros. That's a huge clue right there. It tells us that row was totally redundant. It didn't have any new information. We've just simplified the matrix to reveal its true underlying structure. You know, this whole process, it has a fancy name, Gaussian elimination. But honestly, it's better to just think of it like a recipe. First, your goal is to get a 1 in that top left spot. That's our pivot. Next, you use that 1 to wipe out everything below it, turning them into zeros. Then, you just move down a row, over a column, and do the whole thing again. It's a really systematic way to clean up the matrix. So, after all that cleaning up, look at what we're left with. 2 rows that still have numbers in them, and 1 row that's completely zeroed out. Now, all we have to do is count the non-zero rows. 1, 2. Boom! The rank of this matrix is 2. It has 2 dimensions of power. All right, so the rank tells us about a matrix's power. But what about its personality, its core identity? For that, we need to find something that doesn't change when the matrix does its thing. This is how we find its true direction. Imagine a matrix is like a transformation machine. You feed a vector into it, and it gets pushed, pulled, stretched, and rotated all over the place. Almost every single vector you can think of gets knocked completely off its original line. But, and this is the really cool part, there are these few, special, almost magical vectors that don't get rotated at all. They stay right on their original path and are only stretched or shrunk. These special vectors, we call them eigenvectors. They basically represent the true direction of the matrix, the axes where its transformation is the absolute simplest. And the amount they get stretched by, that's their partner, the eigenvalue, which we represent with the Greek letter lambda. So you have the direction and the stretch factor. Together, they are the core identity. So how do we actually find these eigenpairs? Well, it's another 3-step recipe, and it's pretty straightforward. First, you set up this special formula called the characteristic equation. Its only job is to help us find those stretch factors. Second, you solve that equation for lambda, and the solutions are the eigenvalues. And finally, for each eigenvalue you found, you plug it back into a second equation to find its partner vector, x, and that gives you the eigenvector. Okay, let's make this real. For this particular 3x3 matrix A, once we apply that characteristic equation from step 1, we get this beautifully simple result. That whole complex matrix has been boiled down into a single clean polynomial. And solving this equation is a piece of cake. I mean, what values of lambda make it 0? Well, pretty obviously it's 1, 2, and 3, and just like that, we found the secret stretch factors for this matrix. These are its eigenvalues, the very core of its transformative power. Okay, now for something that is just, well, it's truly profound. It turns out that every single square matrix has to follow a secret rule, a rule that it actually creates for itself. This idea is known as the Cayley-Hamilton Theorem, and it's one of the most elegant concepts in all of linear algebra. So, the theorem states, simply and powerfully, that every square matrix satisfies its own characteristic equation. Okay, so what on earth does that even mean? Let's break it down.
It means we can literally take that characteristic equation, and everywhere you see lambda, you can just swap in the matrix A itself. So lambda cubed becomes A cubed, lambda squared becomes A squared, and on and on. The only little trick is that the constant number at the end gets multiplied by the identity matrix, I, and the result will always be the zero matrix. It's wild. The matrix literally obeys the exact same law as its own eigenvalues. It's this deep hidden connection.
So we found the matrix's power, its true direction, its secret rule. But why should we care? What's the point? How does knowing this identity actually help us? Well, this is where it gets really practical, because it lets us crack the code of one of the most common problems in all of math and science, systems of linear equations.
Here is the big question. If you have a set of equations, how do you know if there's even a solution to find? Before you waste hours calculating, can you tell if you're going to find one answer, infinite answers, or no answer at all? Well, that very first clue we found, the rank, it holds the key.
The method for this is just brilliantly simple. We create two matrices. The first one, matrix A, just contains the coefficients of our variables. The second one, called the augmented matrix, is the same thing, but we tack on one extra column for the constants on the other side of the equal sign. Then, we find the rank of both.
And this table tells the entire story. If the ranks don't match, game over. There is no solution, the system's inconsistent. If the ranks do match, then great. There's at least one solution out there. And we can even go deeper. If that rank also happens to equal the number of variables you have, there is exactly one unique answer. If it's less, you've got infinite solutions.
Think about that for a second. Just by comparing these two little numbers, the ranks, we can predict the outcome of a really complex system of equations before we do any of the hard work. That is the real power of understanding a matrix's identity.
So there you have it. We started with what looked like a simple grid of numbers, and we completely decoded its identity. We found its rank, which measures its power and its influence. We uncovered its eigenvalues and eigenvectors, which define its core unchanging direction. And we saw how knowing this identity gives us the power to understand and predict the behavior of really complex systems. We've seen that underneath a seemingly chaotic or complicated surface, there can be a simple, elegant identity just waiting to be found. And it really makes you wonder, doesn't it? From economics to physics to computer graphics, what other complex systems are out there in your world just waiting for someone to come along and decode their true identity?